Okay, today I'm gonna show how to make a new platform in TinyOS. We have a new MSP430F5342 that we want to integrate and make a new platform and actually program it using mspdebug. And to do all of this, we're gonna use our new Weasel repository's virtual machine that has everything set up for TinyOS development, and we are actually using the TinyProd repository. So we're going to base it off from it because it has some of the latest MSP430 code that has not merged into TinyOS main yet. So initially I'm not going to use Eclipse to do all of this because it's easier to do it all on the command line. But once we have the platform ready, I will show how to use Eclipse and mspdebug to actually debug your platform. This is all on the fly, so expect some misshapes, and I have actually not done this in a while, so there will be some errors that we will have to correct while we're going. I hope this will be a good learning experience for you. Okay, first let's go into TinyOS production environment. We are actually not using the regular TinyProd, but if you look at the branches, we are actually on the MSP430 internal, which is the free-for-all repository if you are familiar with the TinyOS prod repository itself. So the first one is we have to find a other platform that's similar to what we actually want to do. So let's go and look in the TOS platforms directory. In here we have all the different platforms that exist right now, and one that's actually fairly similar to what we want to do is the MM5S. In here, this is the setup for this particular platform, and if you actually look at a hidden file, so if we show all the different hidden files, there's one hidden file, the .platform file, which is actually one of the most important platform files itself. So if you look at this particular file, we can see that this is one of the platform files that actually includes and adds all the different sub-repositories. And what we are really interested in is this x5xxx directory, because that's saying that this uses the new 5000 family MSPs. More particular, this platform uses a 5438A. Very similar to what we are doing. Okay, so let's go back. Let's call this platform. We first create a new platform directory. Let's call it Weasel for now. And we have just an empty directory, and let's copy over this platform directory, platform file in here. So let's edit this. Let's add comments to all of this. We don't need this for right now. We can keep this for now because we do have an MSP430 with pins. We don't have any of these, but we want to keep a timer, a serial, a power, and the printf libraries in there. Okay, there is some magic happening down here. Let's change this to the 5342. Target is MSP and the different task schedulers that we want to include. And here are a couple of the different setups that we have to do for the seal machine. All right, the platform is set. Now, if we go and try to actually build this, I create a new tab so that we don't have to switch around all the time. And we try to build a null application, so make Weasel. We can see that, oh, there is no Weasel platform, even though we just created a Weasel platform. But that's actually not where the whole key is to the whole platform. So what we actually have to do is in support make. This is the whole make infrastructure. This is where all the different platforms really reside. So if you type make epic, it will, for example, use this epic target file in here. So we have to create a similar one for the Weasel. So let's copy the MM5S target and call it the Weasel target. Let's edit this. So they call it the platform is the MM5S, so we call this the Weasel. The MCU is a 5342, and what we want to include is the platform itself, so a Weasel platform directory in the make directory, plus the MSP430 directory, and here we want to call this the Weasel. Alright, so that will be it. Let's try it again. We go over into our null directory, make Weasel, and it compiled now. That's great, but there are still a couple of errors that happen. So it needs a platform.h file, a hardware.h file. We can easily provide them if we actually switch back to TOS platform Weasel. We just copy them from the MM5S platform.h. Let's look at this file first. It's just an empty file. And if you look at the hardware.h, there is a couple of more things in here. This is basically a definition of the different power states and what kind of hardware that we have, pin assignments, radio pins for a CC2420 radio, and FIFO pins themselves. So actually we don't need any of this because we don't have a radio. We do want to keep these LEDs for now though. These pins are actually wrong. We will have to change them later on. Alright. Let's try this again. As we can see, we still need a component platform C. This is one of the initializations that we need to do, platform C. If you look at this, this is one of the initial hookup libraries that basically links a couple of different peripherals together. So it provides an interface called platform init, and uses an interface and peripheral in it. So it hooks up the different platforms, it connects the pins, the LEDs, and the USCI and the clock system together. So if we try to do a make now, it will start complaining about these other files. So the platform P, the pins, LEDs, USCI. Again, let's go and see if we can find them. Platform P, that was an easy one. It uses a platform version, major minor build. Boot magic, I have no idea what this is, we will have to find this out. And this uses a couple of other new peripherals. It starts initializing different things, the different pins and different. So it initializes, it turns off the watchdog timer, initializes the GPIOs, LEDs, clock, and the peripherals. Alright, again, let's go and see what this did. So we now need a platform's pins C. And if we go back into here, we won't see a platform pins. So that's actually nicely stowed off in the hardware pins directory. So let's go and copy all of these. Hardware, actually first, let's make a hardware directory, and then hardware, let's copy the pins over, because that's most likely what we will need. What else do we have here? Let's copy the ADC over, copy clock, and the USCI, which is the UART that we have. Okay. Next, let's go into the hardware directory. Let's start with the pins, verifying that everything is okay here. So this is just a simple initialization. And in the initialization, what does it do? Nothing at all. Excellent. All right. That was easy. Next, let's look at the clock, because that's also an important setup to do. It basically brings up all the clock systems in the background, so the configuration is very simple. And if you look at this one here, there's lots of text that we probably have to go and read through in detail and change this to the right clock system that we need. This is basically code that brings up all the different clocks, and we just leave this for right now and just hope that these two MSPs are similar so that we can at least get a blinking LED up and running. Alright, quick check at the license. This is a typical BSD license, so thanks Eric. We can reuse this and actually modify it as long as we leave his name and copyright notice in there, which is nice. Alright, so clocks are good, pins are good. The USCI is a little bit more complicated, so we leave this out for now. And it's probably broken. Same for the ADC, that will take a little more time to actually get it up and running. So let's go back into the null application, and we still don't have these files in there. So now we have to go and dig and check to see why you couldn't find those. Alright, so most likely this is in the .platform. If you remember, we didn't have, we want to enable the clock LEDs and the pins because we looked at them. We leave USCI out, we leave the buttons and the ADC out because we don't need those yet. So now we found some of them. Still can find it. Okay, does need the USCI directory too. So let's add this one here. This should get rid of some of the errors. And now we are further. Okay. Still can't find platforms LEDC. So let's see where this is. This is the platforms pin. Oh, the LEDs directory. Okay. We want to go and get that too. And again, in the .platform. Oh, we have them there. Okay. I just forgot to copy them over. So that got rid of that mistake. And now we have problems with the USCI. Since the MSP430 that we are using probably has a lot less UARTs than what this bigger neighbor has. So more specifically, it complains that the UCA 3 CTLW0 is undeclared here, not in a function. So I'm gonna pause the video right now to dig a little bit around and see what I find, and I will come back once I know what's going on. Okay, I actually decided to show you how I go about finding out this problem. And if we look back here, the one thing that we notice is that it tries to include the MSP430 USCI A3P. So this means that this is the third USCI on this particular MSP, and I'm pretty sure that the 5342 does not have 3 USCIs but only 2. So how can we find this out? Well, we have to go and get the data sheet. First, let's look up our data sheet, MSP430F5342. Having this data sheet handy will be useful later anyway. So we have here the family user guide. Let's get that one for one. Plus we will want the data sheet itself. Alright, so let's see, this is downloading. So this is the 5000 and the 6000 family user guide. This one here has everything inside of it that we want to ever know about this particular chip. And let's save this in our downloads directory for now. Here is the particular data sheet, so let's save this guide too. And call it good. All right, so let's first see. Well, and here we already have the answer. We have a USCI A0, USCI A1, and a USCI B0. All right, so that's a good hint. Let's go into the hardware USCI, and let's start looking at the platform USCI map. If we go and look in here, let's change this to MSP430F5342. This is actually connecting the different pins. So we have the A0, B0, A3, which does not exist in our particular system. So we just delete this one out. Let's see what we have in the platform SPI. Oops. This is a very generic, just a resource request. Platform SPI C. Again, this is just linking up the B0 SPI, which is perfect for what we want to do. Let's look at platform serial. Again, very generic, just bus arbitration. And serial C, I suspect in here we will have to do something. Nope, this is just looking at the UART A0, so I guess we are good. Let's see what happens when you compile this. It couldn't find UCA0 RX TX CMOS SOMI and clock. Alright, I remember we deleted those out in the pins directory. So let's quickly check. Must have been the hardware, oops. Hardware.h. Yeah, these pins were down here and we deleted them, so let's get them back. Go into MM5, splat hardware H. No, they're not defined in here. So then let's find them. All right, they're in the platform pins directory. Let's look at this file. Not entirely sure what's going on here right now, so I am, because I see that we have them in here, but we have them uncommented right now. So I'm suspecting that these are actually not the right maps. Alright, so let's go back. Let's see. This is in the maps directory. So platform USCI map. We include the MSP430 USCI H. And it complains line 48. 48. You can find UCI0RXD, UCI0RXD. So in the GIO document, and that's the HBL MSP430 General IOC. So that's actually where we have to go and look at. Well, now comes the big question. How can we find this particular file very quickly? Now, I know where it resides, but if you ever find one that you don't know, use your good old find in the TOS directory. Name would be, oops, that's not the right file name. We go to the right file name and see, and there it is. So if you look at the chips pins HBL MSP430 General IOC directory, in here we can go and look for this guy again, the UCA0RXD. So if we go and search for UCA0RXD, then we see that UCA0RXD is if it's defined as a 241, 261, and 26X. Alright, that's good, but that's not our chip. Alright, here we go. This is for the 513, 612, and 613 chips. And there are some more in here. 54XA, 54X. And this is the part that we copied it from. But our chip is actually different. So what we really have to do is actually modify this file and add the pin definitions for our particular chip. Okay. So why don't we just make a copy of this. And add it actually above here because it should be in between these two. So X5 family MSP430 F5342. Right now let's just do only the 2 without any modifiers. There are other ones in this category, but I'm not gonna look into them. In particular, 54342. Alright, you should be using the part A, non-A are buggy. So that's not for us. So if it's defined 543X, then we do all of these. Now, we do have to go and change them, of course, and there's actually a second section down here that we also have to adapt. And I will make these modifications now without having it recorded, as this is probably reasonably boring. And we can delete all of these. Clean up this one here. And we call it good. So let's see if we can actually compile null now. Apps null, make weasel. And still errors. So it couldn't find UCA0TXD. Now we need to go and look and start digging of where these hash defines are actually defined. Hopefully we will find that quickly. Because UCA0RXD should be defined here, and we also linked it to something, so it should be there. But most likely this hash defined here is not defined, so what we should do is, let's go take this hash define and see where this was defined. Let's grab a new one. I actually don't expect it to be anywhere in here. See, this is the NC files, and they just use this hash define. So this hash define is probably somewhere within the MSP430 code itself, which is in opt MSP. Here we go. So if we go into the includes here, if you looked at MSP430F5342, the one that we want, let's make this a little bigger. Let's see what hash defines we have. So we have the hash define of the actual one. But not of the family itself. So let's see if we can find one. X53. And we couldn't find that. Alright, that's interesting. Because all the other families define one of these things. F5, 4, 3, 1. Let's do 3, 6, 8. You see that these are actually defined different. They define a hash define for the family, while the one that we want only hash defines the actual chip. So a little bit annoying and unfortunate. So let's see if we have a family definition on here. No, that doesn't exist either. So we really have to use our hash define. That's unfortunate, but that's how it is. So in here, nope, we don't use this one. We use the hash define from our include file that will be included because this is our particular chip. And let's just check what happens with the other ones. Yeah, they have the. So let's just add them all in here. So the 40 1 and for 2. So here we do exactly the same thing. This. So this is all the hash defines that we have to have. Let's search again for the other ones. Here, 4, 5, 3, 4, 2, 5, 3, 4, 3, 4, 1, and MSP430F5340. All right, let's see, this should now work. And voila, so we are only at TA1 CCR. That could not be found. 1053, we're getting closer. 1053. That's the wrong destination. All right, so here comes another trick. What you can actually do if you run Vinylman here, you can actually do a make inside of Vim, and it will show you the error and actually jump to error. So make weasel, and it tells us it's already open. So let's actually not open it again, because that would create inconsistencies. So if we do this, make weasel, okay, TA1 CCR 1 could not be found, so we probably forgot it up there in this first definition. Yes, we have TA1 ZCR 0. Oh, maybe I was wrong on the other one. It's 1, 0. That's correct. Okay. So let's go back to where we were. TA1 CCR 0 is here. All right. Let's build this again. So TB0 CCR 1 could not be found. Let's see. This is a more ominous one. So it tells us that all these particular links could not be found or are not connected. This is interesting. Let's see if we made a mistake here. Ah, yes, because we have them in here, but not in the bottom anymore. So let's actually remove them for now. We can see if we really need them later on. We can check them in again. Still complains that TB0 CCR1. Oops. Did I start? No. Very good. Okay, let's see. Why is TB0 CCR1? That's right, because it's in the books, but where is it? TB0, it's on P5.7. Alright. We can actually connect this. This is us. So let's do TB CCR1. TB0 CCR1 is on 5.7. P5.7. That error is gone. And now we only have an error with P7 select, which doesn't exist. So, what is this exactly? Okay, this is to initialize. If you notice, we are back in the Weasel hardware clock platform C, as I mentioned before. And we probably had to look at this later on. So in this case, for this, where we copied this from, the crystal was on pins 7.0 and 7.1. This is not the case anymore for us. The pin is actually on P5.4 and P5.5, X in and X out. And I'm not even sure if this is the high-speed clock or the low-speed clock. We have to check into that. Okay, there is an XT2. Okay, this is the high-speed clock, this is the low-speed clock, so it's on P5.4. And so this would have to change to 5 bits 4 and 5. So this has to be checked. XT1 is on pin 5.4 and 5.5 in our case. Let's do this again, 5.4, 5.5. All right. So this is configuring the UART. And here again, it goes into, this needs to be bit 5 or bit 5 and 4. This is actually a very badly indented file, so let's just fix all of this. P5 cell to find it again. Okay, this should be good. Alright, let's see what happens. Make Weasel. Oh! And there we go. First application of not doing anything compiles. So next step, let's see what happens with link make Weasel. It compiles. This is very exciting. The problem is that our LEDs are actually not set up properly, so we first have to find out on which ports we have our LEDs for the particular hardware that we're looking at. So I pulled up the schematic of our device that we're actually trying to program. You can see here the PCB with a nice little breakout board with a couple of diodes over here, which are actually LEDs, VCC connectors, and the programming port here on the side. Down here we have the schematics, so we can actually look up everything. And this is actually the board itself with the MSP430 in the middle, small little breakout board with power connectors connected all around. So the first thing we want to do is connect the LEDs properly, and if we zoom in here to 100%, you can actually see that these are the LEDs with some current limiting resistors. We have a crystal on here that we can actually use to get a nice 32 kilohertz clock signal into our MSP. Plus here on the right hand side we can see that the LEDs are hooked up to port 6.3, 6.4 and 6.5. So let's go into our TOS directory. We want to be in our platform Weasel. We go to hardware, LEDs, platform LEDs C. You can see that here the LEDs are actually hooked up to port 10, so this is actually not correct. We said this is at 63, 64, and 65. Oops. Let's quickly verify this. 6.3, 6.4, and 6.5. 6.5. So 6.5, 6.3, and 6.4. Okay. So we save this. Let's see if our Blink application still compiles. And it does. And the nice part is we can actually see that this is 2.5 kilobytes in ROM, 110 bytes in RAM to make this application work. So the next step would be to actually program our MSP430. Now we are using an application called mspdebug, and mspdebug supports pretty much all the MSP430 programmers out there. The one that I really like is this small little EZ430 UIF. This was from the Easy Chronos programming development kits. There are a lot of different ones out there. There is one from the RF2500 and one from the EZ430 RF2013. Unfortunately, all run different software on them, so either you upgrade the older ones to a newer software version or else they won't work. Now it turns out that this one here from the Chronos watches actually works and knows the F5342 microcontroller. So what we do is we take our board, we make sure that pin 1 connects with pin 1 on our board, plug it in like this, and then we put it over on our USB port. Since we're working in a VM, we want to make sure that we connect it to our virtual machine, and with a LS USB we make sure that the 0451 is the Texas Instruments code, and then the F432 is the UIF from the EZ430 development kit that we can use to program all of this. So in order to program this, we can see that our application got actually built in Weasel main. So all we have to do is call mspdebug. RF2500 is the driver that we want to use, and we want to program build Weasel main exe into this application. This will start. It found it, it set everything, but it failed to identify our device. So let's check if everything is alright with the connections. Everything looks right. try this again. Okay, this time it worked. It found that it's which MSP it is. It has 128K of RAM, 10K RAM, and it's actually programming the 2K right now into Flash. And that was it. And I extended the cable a little bit, and you can see one of the LEDs is actually blinking, and the others are not, and I will have to check what's going on. But that was basically it. The next part of this tutorial will be how to do all of this in Eclipse, how to write your application and use this system now in Eclipse. Okay, the next step is programming the MSP430 using Eclipse, Yeti tool, and some debugging configurations to use mspdebug to actually program everything. Alright, so on the left hand side we have Eclipse Setup, so let's start it. And the current Eclipse is set up using the Yeti 2 TinyOS packages. There are a couple of things that don't always work perfectly, and I only have been experimenting with this since yesterday, so let's hope this all works out this time. First thing, we create a new, we want to verify that all the setups are actually still there. So in Windows, Preferences, TinyOS, we can look at the cache strategy. There are already a couple of errors. Let's, an error occurred. Okay, this is not going to work at all. Okay, let's just try this again. Interesting. Sometimes rebooting and restarting Eclipse works, so did also this time. Alright, so verifying the environment, in the environment TinyOS Unix environment, we make sure that the TOS root is actually set to the root directory that we want to use, in this case the TinyOS prod directory, which is what we want. And then let's start a new project. We base it off of an example, TinyOS example. One of TinyOS wrapper, we give it a name, let's call it Weasel Link. The platform, if you go in here, we see the Weasel actually was found as a platform, so the TinyOS Yeti 2 plugin for Eclipse actually searches all the different possible targets all the time, and we want the Blink example, and it will take it and put it into the workspace as a Weasel Blink directory. So let's finish this. It asks us if we want to switch over into the perspective, and yes, we do want to do that. Alright, so we have a test blinky here. That was from a previous test. I'm going to delete this and everything on the disk too, so that we only have one project. This is the Weasel Blink example, and if we actually open it up, we can see in here this is all the different blink and everything that seems to be working. So this is good. Sometimes, for some reason, it doesn't find these interfaces. Other times it does find them. I have not found out why yet. So right now it says 7 errors, but they're not actually errors. Sometimes it's just fine and everything works okay. Alright, so the first step is we want to build this application. And building it is slightly different from regular applications, so we actually have to run it. We want to make a run configuration. And what we want to choose is a TinyOS build run configuration. We can choose the project that we want. We have the application as the default application, that's fine, includes platforms. We just want to make sure that it's the Weasel platform. Sometimes this is not right, and then you can just go to custom only and select the platform you want, but for us the Weasel is actually the right platform. And in extras we want to select debug, because we want to debug this using MSP430 We don't have any sensor boards, no special environmental variables we want to set or anything else that we have to run. So we apply this and we run it, and down here is the output. Let's see, looks like everything worked. Made a file and it saved it in buildweasel main.exe. So if you go here to build, this is actually the wrong build directory. So this is not the one that we want. We want this one here, build weasel, everything is here. So this directory here, we can delete. It's this one here, build weasel main.exe. Alright, next we want to actually program this into our system, and for that what we do is we run a external tool. So we say in external tools configuration, I already have one here, but I'm gonna delete this to make sure that we create a new one. So we do create a new one, we can give it a name, mspdebug program, and the location, this is the location where the mspdebug is located at, that's in user local bin mspdebug. Found it, it says run a program. The working directory, we want to run this in the blink build weasel directory. Makes the arguments a little easier here. Arguments rf2500, so the driver we want to use, and we want to execute proc main.exe. What this will do is it will actually just program our device using mspdebug. We could refresh the workspace, we could actually build the project, we can have environmental variables that we want to set, or some other stuff that you can set. So let's connect our node. Let's click on run, and we see down here what happens. It's starting up, and nothing's happening right now. It's usually a bad sign. So let's try this again. Run mspdebug. USB util unable to find the device. So let's first check, since we have a virtual machine sometimes. It disconnects our USB device, and this is also the case this time, so we reconnect it. And let's try to run this again. Still unable to find it. We can try this again. There we go. Found it. It's erasing it. It's rewriting it. It's programming the Flash code right now. And it will have 3 more small little sections that will be programmed, 2 bytes, 128, and that was it. And the board is blinking again. So that was basically programming the whole code now using a binary that was compiled. If we close this one here, so if you look at the compiled program again, you can see that the GCC executed actually used the -G flag, so this now has debugging information. So the next step is we configure a TinyOS debugger session. So in this case, let's delete the session that I had here before. So we want to double click on it, get a new debugging session. The project that we want to debug is the Weasel Blink project. The binary we want to use is a main GDB proxy. We want to use a user-defined application, namely mspdebug rf2500, and then we want to execute the command gdb inside mspdebug, which will basically wait and listen on a port in the background. Debugger configuration, we want to stop at main. We want to use msp430 gdb. You can execute gdb in it. We don't have one configured, but you could if you wanted to. Right now, let's use a verbose console, and here at the bottom, we actually need to configure to the port that it has to connect, and mspdebug is actually listening on port 2000. So sources, we can add more source paths, and the commons directory again. Alright, so next step is we run debug. We can see down here It's now listening on port 2000 and GDB connected to it. Yes, we do want to launch the environment, and something didn't work. Actually, what happened is it did stop at the right location, but it couldn't find the sources. So it stopped at the real main P. Now, this is still one of the problems I have to find out. I don't know why exactly can't find it, because other files you probably could find. Let's see what happens if I add the real main P, which is in TOS. I think this is in system. And if you look here, its real main P is right there. These are subfolders. Okay, and no, we still could not find the sources. So this is still one of the things that I have to find out. What we can try to do though is let's set up a breakpoint right here at the beginning, and let's run and see what happens. Nope, that did not work. So if we stop it, I can see the code actually stopped. We're somewhere in MCU sleep. So there's still a misconception between setting breakpoints. So if I do a breakpoint here in this call, if I run it, I can see that the LEDs blink again on the device, but the breakpoint never gets hit. And I'm not sure why exactly this happens. Something I still have to find out. So I found the problem and I fixed it, so let me show you what we have to do. There is one more step of sources that we actually have to include into a project. So once Eclipse is started up, the Weasel blink, what we have to do is we actually have to add the TinyOS sources to it. So we have to right-click it, properties, and here in the TinyOS sources, we actually have to add this tinyprod directory. So what we do is, instead of adding a folder, we can't do that because these are just the folders that are actually inside our project. What we want to do is we want to link a source, and we want to go find the tinyprod directory, and we link that now into our system, and we hit OK. It shows up here as a linked folder. Eclipse now will start indexing this, so this will actually take a while because it creates a fairly big tree that is actually linked into the system now. But what we now can do is, if we go and debug our system, we see that a lot of things are waiting. Again, let's see what else is actually going on here. Let's call this one here. Don't exactly know what this one does. What I really want to do is launch my debugging session. Let's set up a initialization failed. So let's try this again. Still didn't work. So I do that typical trick of closing, plugging it back in. We wait. Looking at the debug environment. There's some actually running, so let's remove all of them. Start a new session. It's bound to port. It's initializing, and it stopped at main. There we go. This is all we have to do. You can now start debugging. You can run it. You can step over. Let's go and try out to set an actual breakpoint in our Blink application. So let's set breakpoint debug. Breakpoint here. Disable it. Let's enable it. Make sure it's set. Let's run it and see if we ever stop in there. And we do not. So that's still something we have to find out what's going on exactly. But at least you can start stepping through the whole sources from the beginning, so that works. Most likely what's happening is that the ports of the debugger actually get configured and get killed so that the debug actually loses their connectivity to the system. That will be it.